Hi guys, welcome to the 11th class of this course. In the last few classes, we talked about the Lagrangian equation of motion. Specifically, in the last class, we saw whether we can treat the non-conservative forces in this framework of Lagrangian equation of motion, especially the forces, the dissipative forces, the frictional forces. So whether those kind of, or how to treat those kind of forces in this framework. After that, we did a very simple problem that motion of a particle in space while treating the coordinate systems as a Cartesian coordinate system. So there we solved the equation of motion. So today we will first do the same problem, motion of a particle in space, but we will take the coordinates as a polar coordinate. So we will see that while changing the coordinate, we can generate some new kind of forces. So let's look at that. So these are the applications of Lagrangian equation of motion. Single particle in space in plane polar coordinate. In the last class, we talked about the same problem, but in the Cartesian coordinate. So this is the x-axis, y-axis and z-axis is coming out of the plane of paper, z-axis. This sign means there is an axis coming out of the plane. So in this coordinate of the particle in this plane is defined by this r vector. So r is the coordinate of the particle. Mod of r is r, and the angle it makes with the x-axis, that is called theta. So then if we write r as x I hat plus y j hat, so this is the x I hat, it's going x length along I hat direction, along positive x direction, and then y length along the positive y direction. In this way it will get at this point. So then this x is basically r cos theta, and this y will be r sin theta. So x is r cos theta and y is r sin theta. So in that case, x dot will be r and theta. If the particle is moving with time, then both this r and theta, they are changing. So in that case, the time derivative of x, that will be r dot cos theta plus, or r, so the derivative of cos theta, that will be minus sine theta. So there will be a minus sine here, minus sine theta, d theta dt, that is theta dot. So minus sine theta, theta dot. Let's write theta dot before sine theta. Otherwise, it will create confusion. R sine theta, r theta dot sine theta. Similarly, y dot will be r dot sine theta plus r theta dot cos theta. Derivative of sine theta is theta dot cos theta. So in that case, the kinetic energy T will be half m x dot square plus y dot square. So x dot means Vx and y dot means Vy. So this means half m r dot cos theta minus r theta dot sine theta square plus r dot sine theta plus r theta dot cos theta square. So then if we do the squares, we will get r square cos square theta, and here we will get here we will get r square. So here we will get from the first one. So from this term we will get r dot square cos square theta, and from this term we will get r dot square sine square theta. So then this is cos square theta plus sine square theta. So for squaring this term, we will get r square theta dot square sine square theta, and squaring this term, we will get r square theta dot square cos square theta. So if we take take r square theta dot square common, we will get sine square theta plus cos square theta. And then there will be two terms which will cancel each other. So one term coming from this square, which will be 2r r dot theta dot sine theta cos theta, and another term that will come from this square. So that will be plus 2r r dot theta dot sine theta cos theta. Now these two terms will cancel each other, and this sine square plus cos square theta is 1, and this is also 1. So what we will get is the kinetic energy in this plane polar coordinate. It will be half m r dot square plus r square theta dot square. This is the kinetic energy in this plane polar coordinate. So what we are trying to do is we are trying to write the Lagrangian in this coordinate. So that's why we first got the kinetic energy, and then let's see what we can do. So while deriving the Lagrangian equation, we use intermediate in the intermediate step. We got an equation like del t del qj dot pdt minus del t del qj equal to qj. But this qj is the generalized force. Generalized force. So now we have this kinetic energy. So we will see that what will be the form of this generalized force. in this plane polar coordinate. So if we have a force, so if in Cartesian coordinate, the force is F, then in plane polar coordinate, Q. So in plane polar coordinate, we have here we have two variables, two kind of variables. So as we are in the plane, so in that case, we have so we have two generalized coordinates here, which is r and theta. So corresponding to two generalized coordinates, we have two generalized forces, which will be qr and q theta. Now, how to derive them? So qr will be F dot del r del r. That's how the generalized forces are defined, if you can remember. And q theta is F dot del r del theta. Now, if you look at this r vector, you can write it like r hat. So now if you look at this dr vector, that will be r hat dr plus theta hat r d theta plus z hat dz. But since we are in this plane polar coordinate, we will not talk about this z component. So it is not necessary in our problem. So in that case, this del r vector by del r, that will be, so from this part, del r by del r, it will be r cap, and del r vector by del theta, it will be r theta cap. So in that case, what we are getting is this theta r generalized force along r radially outward direction, which is F dot r hat. That means Fr. Sorry, is Fr. And this component, it is F dot theta hat times r, which will be r f theta. What is Fr and f theta? So if we write the force in plane polar coordinate, then the force will be Fr r hat plus f theta theta hat plus fz z hat. Okay, so these are the generalized forces. These are the generalized forces. So now we have the term kinetic energy, and we have, so in this equation, if we call it equation, let's say this is equation 1, this is our equation 2. So from equation 2, we can write the equation 2 in r direction, and then we can write the equation 2 in theta direction also. So from equation 1, so no, from equation 2, what we have is, so if we do along the r direction, so then we will get del t del r dot minus del t del r equal to qr. Okay, now what is del t del r dot? Let's look at this equation 1. So here in the second term there is no r dot dependence. R dot dependence only here in the first term. In that case, if we derivative the kinetic energy with respect to r dot, we will get, so the 2 will come, and this 2 and the 2 coming from this square, it will cancel. So we will get m r dot del r del t del theta del r dot del t del r dot will be m r dot. Okay, so we will get ddt of m r dot minus del t del r. So what is del t del r? Now again, let's look at this equation. So there is no, in the first term, there is no r dependence. The r dependence is only here. So again, we will get a 2 if we derivative this second term with respect to r. With respect to r, and the term, so del t del r would be then m r theta dot square. Okay, m r theta dot square. And what is qr? Qr is basically the fr. What is ddt of m r dot? M is a constant, then it is m r double dot equals to m r theta dot square equals to fr. So now look at this equation. What is r double dot? R double dot is the acceleration along the radially outward direction. So m r double dot, that is mass times acceleration along radially outward direction. And what is fr? Fr is the force acted on the object along the radially outward direction. So here we cannot directly apply Newton's second law, that is force equal to mass times acceleration. So as we change the coordinate from Cartesian to plane polar coordinate, we have another term in the equation of motion. So this new term, it is called the centripetal acceleration term. Okay, so this r theta dot square is the centripetal acceleration, and m r theta dot square is the centripetal force. So we are not in the inertial coordinate frame anymore. So we change the coordinate from Cartesian to plane polar coordinate, and we are in the non-inertial coordinate system, non-inertial frame of reference. As a result, we are getting this centripetal force term. So we are not directly use this Newton's second law of motion. We need to consider the centripetal force, which is a kind of pseudo force. Okay, so this is the equation of motion along r direction. So let's look at the equation of motion along the theta direction. So from equation 2 along r direction. So here from equation 2 along theta direction. So let's look at equation 2. Okay, this is the equation 2. So then along theta direction, we will get ddt of del t del theta dot minus del t del theta equals to r f theta. That is the q theta, generalized force along theta direction. So here in this equation, this force, this is not the uh, force in the coordinate, in that coordinate. It is a generalized force. So this is not f theta. This will be r f theta. This is a generalized force. Now, if we calculate this from equation 1, so we will get ddt of del t del theta dot. Now, what is from equation 1, what is del t del theta dot? There is no theta dot dependence in the first term. So only theta dot dependence in the second term. And if we do the derivative with respect to theta dot, we will get m r square theta dot. So we will get m r square theta dot. And minus del t del theta. So if we look at equation 1, there is, if you look at equation 1, there is no dependence of theta in kinetic energy. So del t del theta will be 0. And we have this r f theta. Now, what is m r square theta dot? If you remember correctly, this is the angular momentum. So m r square theta dot, this is the angular momentum. And this will be then, so rate of change of angular momentum. So ddt of angular momentum, that means this is the rate of change of angular momentum, which is termed as the torque. So this will be the torque. So we write torque by N, and this we write angular momentum by L. Let's write it by curly L, because L is also for Lagrangian we use the L. So let's not confuse it with Lagrangian. So then the equation becomes ddt of the angular momentum will be torque. So by changing the coordinate system, we are getting this centripetal force and we are getting this torque equation. But in the Cartesian coordinate, everything was just force. So everything follows Newton's second law perfectly. So now let's look at another simple problem. Which is a Toots machine. So let's say we have a pulley which is rotating with respect to its axis. So this point is fixed, okay, and it's rotating like that. And this length is negligible compared to the length of the ropes. So there are ropes, and from the ropes we have two hanging masses. So let's take one as M1 and another as M2. So if we take the length of the rope as L and define this distance of M1 mass from this level, from the level of this pulley as x, then this length will be L minus x. The position of M2 from this level will be L minus x. So in that case, the kinetic energy of the system will be half m1 x dot square plus half m2 ddt of L minus x square. Now what is L? L is a constant. It's the length of this rope. It's the length of this rope. So ddt of L will be 0. So in that case, we only have this x dot with a minus sign. But if we use the square, the minus sign will not be there. So we will have half m2 x dot square. And if you take the half and x dot square common, then we will get m1 plus m2. So this is the kinetic energy of the system. And now let's write the potential energy. So let's say let's treat this line as zero potential line. Okay, this line as zero potential line. So in that case, the M1 mass will have a potential energy of, so the total potential energy is a potential energy of the M1 and potential energy of M2. So potential energy of M1 will be minus M1 Gx, minus because this is a zero potential line and M1 it is under this line, below this line, and potential energy of mass M2 will be minus M2 G L minus x. So we got the kinetic energy, we got the potential energy. So what we will do? We will write the Lagrangian of the system. The Lagrangian of the system will be T minus V, which is half M1 plus M2 x dot square plus M1 Gx plus M2 G L minus x. So here we only have one coordinate, that is the position x coordinate. This is our generalized coordinate. So now if we write the Lagrangian equation of motion, it will be del L del x dot ddt of that minus del L del x equals to 0. So what is del L del x dot? Del L del x dot is, so if you derivative this L with respect to x dot, it will be m1 plus m2 x dot. Okay, so 2 will cancel. So m1 plus m2 x dot minus del L. So this del L del x will be derivative of this term. This term will be m1g. So it is m1g, and derivative of this term will be minus of m2g. So, and there is also minus sign here, so it will be plus m2g equals to 0. Now what is ddt? What is this ddt of m1 plus m2 x dot? M1 plus m2 is constant, so it will be m1 plus m2 x double dot. So m1 plus m2 x double dot equals to m2 m1 minus m2 g. In that case, x double dot will be m1 minus into by m1 plus m2 times g. This is the equation of motion of the particle. So we got it from this Lagrangian equation. So you can check whether this equation is consistent or not. So if we take these two masses same, in that case, there will be no acceleration. So if we put these two equal, there will be no acceleration. If we take this m2 0, in that case, this m1, so there is no m2, so m1 will be falling freely under this gravitational acceleration, which is g. So the x double dot will be g if we take m2 0. And let's see what we get. We get this g. Okay, so if we put m2 0, we'll get g. m1 and m1 cancel, and we'll get g. So this is consistent. So now let's look at another problem. Which is a bead sliding on a uniformly rotating wire. In a force free space. So there is no force in the space. There is no force only. So if you can see, if it's rotating uniformly, if the wire is rotating uniformly and the bead is on the wire, then there will be a force of constant, but there will be no other force acting on the bead. That's the force free space. That's the meaning of force free space. So if the bead is if the wire is rotating, let's say the wire is rotating with angular velocity omega, in that case x will be r cos of omega t and y will be r sine of omega t, right? Omega t means theta. It basically represents a theta. So you can check, like, let's say the wire is rotating. This is the x, y coordinate, and the wire is this. Actually, this is the wire. And it rotates like this. So with respect to a axis which is perpendicular to this plane. So in that case, this angle will be omega t. Theta will be omega t. And we will get r x as r cos theta. So r is the position of the bead. So in that case, the x component will be r cos omega t, and y will be r sine omega t. So then the kinetic energy will be half m r dot square plus r square omega square So you can derive it in the same way we derived the kinetic energy for the first problem. which is this. So here the theta dot is basically the omega. Okay. The rate of change of theta, rate of change of angle, which is the angular velocity, omega. So the kinetic energy is half m r dot square plus r square omega square. This is the thing we write here. And omega is constant. That means, I mean, why we are treating omega as constant? Because it's rotating uniformly. So uniformly means the angular velocity. Uniformly means the angular velocity, it is constant. So with constant angular velocity. So the potential energy will be 0 because it's a force-free region. There is only forces of constant, but we are taking this, we are considering it as a one-dimensional motion. So we are already incorporated this constant in our system. So in that case, if we write the Lagrangian, it will be, Lagrangian will be t minus v, which is basically t. V is 0. So we'll get half m r dot square plus r square omega square. Now, if we write the Lagrangian equation of motion, we will get d dt of del L del r dot minus del L del r equals to 0. It implies d dt of what is del L del r dot? Del L del r dot is m r dot. This m r dot equals to, okay, not equals to, minus del L del r. Del L del r means m r omega square. It equals to 0. So if we do this derivative again, so we will get m r double dot minus m r omega square equals to 0. So the m will cancel. Then we will get r double dot equals to r omega square. Now if we solve this, r is a function of time. So if we solve this, we will get r equals to r0 to the power omega t. So r is a function of time. So it says that the bead is going away. So bead is going away from this center exponentially with time. Okay. So this is the solution of this problem. So today we solved 3 very simple problems using this Lagrangian equation of motion. So at last, let me say why this Lagrangian formulation is so important. So we had this kind of 10 plus 2 level forces. We learned about the forces, the Newton's second law of motion. Those are there. We can and use them, and we can write the equation of motion of the particle. We can solve them. So why this Lagrangian equation is so important? It's because it is a scalar equation. And those equations, those are force equation or torque equation, those are vector equations. Okay. So for vector equation, it's very difficult. If we, the more particle we have, the more difficult the problem will be, because there will be forces in different directions. So those are vectors. So in that case, you have to divide it into the components and then add, and there will be a lot of ambiguity while doing in that process. So here we have scalar equation. The Lagrangian equation is basically a scalar equation. You have the kinetic energy, which is a scalar. You find the potential energy, which is again a scalar, and you subtract those, you will get the Lagrangian, and you have the Lagrangian equation of motion after that. That will guide you to solve the problem. So that's why this Lagrangian formulation is so important. Okay. So in the next class, we will talk about the action principle of action, the Hamilton's principle, and After that, we will derive this same Lagrangian equation in terms of the simultaneous principle. So remember here this D'Alembert's principle that we used to derive this Lagrangian equation, it's a differential principle. So in the next class, we will use the Hamilton's principle, which is integral principle. So that's all for today. Thank you.